So here we try to make a screencast to explain Arima model. So in the lecture we have done the we have explained what is Arima model, but in a kind of hectic. So if you think you need more explanation, you can refer to this video, but that's not necessary. So most of things are covered in the slides or in the lecture. So only if you need actual support. So as we said, the idea of Arima actually is to consider the autoregressive part of the of your forecast, and also we add extra moving average from your forecasting errors. So in general, Arima means 3 parts. The first part is here, autoregression part. This is regarding several past period actual data. And then moving average part is to add a moving average regarding your forecasting errors. And integration mainly related the methods to estimate the parameters. So if your data is not stationary, you're not allowed to use the autoregressive plus moving average method. So that's why here we have an integration part. We explain what is integration later. So we start with the Arima model. So the general concept is you forecast the one dependent variable at time t, and then this y is including multiple parts. First is a constant, then we have a linear regression of past several period. So here we call autoregressive. So basically we assume your forecast directly depends on several past periods realized data. Moving average part here is mainly related to forecasting errors. So we actually have separated parameters regarding your autoregressive. So here the P means you consider your forecast depends on past P realized data, and the meaning forecasting errors part is a moving average, but with weights, or it's more like a weighted sum of past Q periods. So that's why here we have 2 parameters. One is called P value, one is called Q value. So there is no difference. That also means no integration. Oh, sorry. And then we can further see the modeling part. So Arima model basically is defined by 3 orders, so which is P, D, so just P value or D value and Q value. So we explained what is P or what is Q in the previous slides. So here you can see the P is showing in your backshift notation of the Arima model. So here means you have a P past real numbers considered. And then D is if you need to transform your data to be stationary, then the D is considered. So here is a Q. Q actually is how many historical forecasting errors you will consider in your model. So backshift notation, so here we see this B value is actually smart way to write your Arima model. Later on, I use the example to show you how this actually is realized. But so far, you just remember if you want to fit Arima model, you need to make decisions about order. So here we want to see PD values should be given. So we need to decide P, D, and Q values. First step. Second step is to estimate parameter values or coefficient of your autoregressive part and moving average part. So we have multiple parameters. So first, phi 1 until phi p is a coefficient of your autoregression model. And then we have a theta, so this is an autoregression model, parameter coefficients. And then we have theta 1 until theta q, so this is a moving average coefficient. And this will be actually read out in your R package. So now we can see next example. So here if you see P equals to 0, D equals to 1, Q equals to 1. So we have a specific model. If it's Arima 0, 1, 1, so basically means P equals to 0, D equals to 1, Q equals to 1. If you replace these actual values or orders in our previous backshift, then you can get a formula here. So we do a quick derivation for this equation. So 1 times yt is yt. So b times yt is here yt minus 1. And then 1 times epsilon t, so you have epsilon t. And theta 1 times b times epsilon t, you get theta 1 times epsilon t minus 1. So in other words, we have b times yt equals to yt minus 1. And then theta 1 b times epsilon t equals to theta epsilon t minus 1. So hopefully you understand the backshift operator b in a better way. So after we get a equation here, and then you replace the theta value by alpha minus 1, and then rearrange this formula. So you actually just open this bracket. You have yt minus 1 plus alpha minus 1 times yt minus 1 minus y hat t minus 1. And then you open the brackets, so you can get yt minus 1 plus alpha yt minus 1 minus alpha y hat t minus 1 minus yt minus 1 plus y hat t minus 1. And then this will be cancelled off. And then the rest equals to our simple exponential smoothing model. So hopefully we can use this example to show exponential smoothing models actually are the special cases of Arima models. So here you can see Arima 0, 2, 2 equivalent with our exponential smoothing model with the additive trained method. You probably ask me, what if the seasonality is considered? Then we have to use non-seasonal Arima models, and we see that later. So then we come to the question how to decide the model order, or in other words, how to decide the D values, P values, and the Q values. So regarding T value here, D value is basically you plot the data and you see how many times you need to difference the data in order to get a stationary time series. The Arima model only considers linear differencing. And if you need a nonlinear differencing, then we have to do that separately. So that's another way. So in this lecture, Arima model is using linear transformation. And in order to decide P and Q values, so we need to use some statistical values. It's called archives information criteria and corrected values, and Bayesian information criteria values. I give this formula later in the slides, but it's better you refer to the textbook sections. And then we continuously talking about how to decide model orders. So the general idea is to start with a small number of p-values. For example, here we have some quick examples you can start with. And you try all these models, and then you choose the best model, and the best model will be your current model. So this is actually evaluated by corrected AIC values. And then based on your current model, you change P and Q value by increase or minus 1. Then gradually you compare more values. And then another thing is the C values. So this C, you could have that or not to have that. So you can test in which way is the best. So in the FPP3 package, so you can always start with the auto fitting. So basically, you just do Arima with a variable, and then you get a reported model. And the reported model already show you the P, Q, and D values. And then you can go to step 2. And then this is also a good starting point. And so we also see the maximum likelihood estimation is used to decide the parameters. So once you decide the Arima model orders, then you basically know the Arima model, and then parameters are required for specific forecasting. So how to estimate the parameter values? We use this method, maximum likelihood estimation. So the general idea is you try the different parameter values, and then you estimate the distribution of your values or your time series. Then you can evaluate probability, and then you can maximize the likelihood to achieve the actual historical time series. This method is very similar with a least squares estimation, but the difference is the method is nonlinear, or we see the estimation is usually more involved than the simple linear regression. So there are different software may give you different estimates, so we do not struggle with exactly same estimates, so we want to have something similar. I'll give you good accuracy and also good AIC values. So we have the textbook example of this Egyptian exports time series, and we want to fit this model by automatically fitted Arima model, and then if we extract the model parameters, we got an output here in the right founted values. So now we try to explain what is a model presented here. So first, you have a Arima model given. So here is basically told us you have a P equals to 2, D equals to 0, Q equals 1. So this is a starting point. Your automatically fitted Arima model orders. And the second step is we also need to read out these parameter values. So AR1 is used as a name of your phi 1, or the coefficient for yt minus 1. And then similar, you have phi 2, and the theta value is here, theta value. So come here. So here, if you know this order and replace the backshift notations, and d equals to 0, so the difference part is replaced by 1. And this is purely autoregressive part, so it's called AR part. And this part is a moving average part. So C is a constant. And the parameter values you can read from this part. And then we replace this phi 1, phi 2 by these different values. The interesting part is here. You open the bracket, you get 1 times yt become yt minus phi 1 times b times yt plus phi 2 b square yt, and then so I can't actually move them around. Let me see if I can move it around. Sorry. So I move it away and then wipe it. So we continuously to open this box. So from here to here, we have actually, so we continue to open this box. In the right hand side of this equation, our backshift formula is C plus 1 times epsilon t plus theta 1 times b times epsilon t. So rearrange this relationship, then you have yt minus phi 1, so continuously yt minus 1 minus phi 2 yt minus 2 equals to c plus epsilon t plus theta 1 times epsilon t minus 1. And then you rearrange this, we get a yt equals to c, c plus phi 1 yt minus 1 and plus phi 2 yt minus 2, and then plus theta 1 epsilon t minus 1 plus epsilon t. And then this basically is your formula. And if you want to continue to rewrite it, then you actually have yt hat equals to c plus phi 1 yt minus 1 plus phi 2 yt minus 2 plus theta 1 epsilon t minus 1. So this is your forecast residues forecast error. So your estimated value is this part. So that's also your Arima model for this specific data set or time series. And now these values can be read out directly. So we have C value is given is 2.5623 plus phi 1 is 1.6764 yt minus 1, and all the other part you just continue to write it. So that's how we get this Arima model. If you want to see what actually is Arima model. So in these things, it looks similar with exponential smoothing model, but just more complicated because now you have more parameters added to different historical data points. Example here, this example, we do not see any seasonality. Can we actually also consider seasonality in your model? So this is about non-seasonal Arima models. You probably ask, what if there is indeed a seasonality involved? So we can actually apply a seasonal Arima model. A seasonal Arima model actually including two parts. One is our currently existed non-seasonal part, and then there is a new autoregression and moving average part represented by the capital PDQ values. So that's basically add a new Arima model, particularly capture the seasonality. And here you can see in the right part, we have a B capital M. So here the main idea is if your cycle length equals to M, then BM times YT equals to YT minus M. So in other words, if T is, we just take example, is Q1, then T minus M is also Q1 related data. So in these things, we particularly add a part of seasonality estimation into your Arima model by add a seasonal part of your Arima. So basically, we are talking about overlapped Arima models. One part is for moving average, autoregression. Another part is particularly for seasonality. The model now become very complicated. So only if you remember or you prefer to know more about this model, then you can go for that. But most of the case, the backshift notation will be sufficient for you to explain. So here we have our shampoo cells, and then we try to fit the shampoo cells into the Arima model. So now you can see the Arima model. So here, automatically fitted Arima model. If you remember, we also use Arima shampoo cells for exponential smoothing. And now you can also see if you use Arima actually consider this data has a seasonality over past 12 months, then with a constant. So after we read these results, you can see the seasonal part. I change the color. So the seasonal part for this model is only related to residues, because the capital P equals to 0, and the capital Q equals to 1, capital D equals to 0. So we only add the seasonal residues into your forecasts. So we can further explain the output of a seasonal Arima model. So we can explain AR1. So this is a phi 1. So this is a theta 1. And the seasonal moving average is actually capital theta 1. So this is how we estimate the coefficient for the seasonality. And then this with drift, that means your model includes a constant. So this is a constant value, or this is a constant. We can directly use a backshift notation. You can see given the low order of the Arima model, so the model actually not that complicated. So we have an autoregressive part, and we have a difference part. We have constants, and then we have a moving average part. So this basically from these three orders. And then in the residues, we actually observe the seasonality. So that's why here you have a seasonality involved with your residues. So this is some intuitive explanations. No need to struggle with mathematical formulas. Just do experiments in your FPP3 package, and then directly compare the forecast accuracy and AIC values. Then that's the way you decide the Arima models. So this is basically about Arima model. In the lecture, we also quickly explained the regression with Arima models. So here we just integrate the regression model and Arima errors. So in other words, if you call a Arima function and with a independent variable, so we actually assume we are doing a forecast regarding regression plus a inter, and here the inter is Arima errors. We do not go for any mathematical models, so here we just want you to know it's possible. Just use Arima model to actually consider the independent variables. So you get more flexible forecasting models. So if you fit the promotion models, now you can see this output shows you have a linear regression model. You also have Arima errors. And the output shows here is a phi 1 value. And then the relationship is here. The inter is a residues of your regression models. And you first go back to find your inter Arima forecast models, and then your y equals to fx plus inter. So basically your yt equals to fxp plus inter, and your inter value is here. And then that's how you get the final forecast. If you are interested, I'm open to discuss. Otherwise, you just remember we go for experimental simulation with R.